Okay, ladies, today we're revisiting independence, that favorite topic of ours. Of course, because the story problems were so epic last night, I had to put this one in. Only in math problems can you buy 60 cantaloupes and no one asks you what the hell is wrong with you. Exactly. Okay. Oh, it's our favorite topic, independence. Okay, so just to refresh, things can be disjoint, meaning they are mutually exclusive. That means they can't happen at the same time. So if events are mutually exclusive, they are not independent. But it's possible for events that are not mutually exclusive, as in not disjoint, they could be independent or they may not be independent. So we, as statisticians, have to check that. How do we check that? Well, we check that using the probability, checking for independence. We say the probability of B given A, and we check and see if that's equal to the probability of B. If those two things are equal, then we know that we have independent events. So let's assume we have some independent events, and let's put this into the multiplication rule that we learned yesterday. So we have the probability of A and B occurring is equal to the probability of A times the probability of B given A. Fabulous. Now, if we know that these two are the same, I can substitute that in. So I get this new fabulous formula. The probability of A and B occurring is equal to the probability of A times the probability of B. So if I have events that are independent, the way that I can figure out if these two things will happen at the same time is just to multiply them together. So here we have an example. In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. So here's the problem. What's the probability that a pitcher throws 9 perfect innings in a row, assuming that the pitcher's performance is independent of his performance in other innings? So we're assuming independence. How do we go ahead and solve this problem? So since we're assuming independence, we can look at each of these events as separate, and we can say the probability of these two things occurring is just the probability of each event multiplied together, which is kind of a cool deal. So we have 9 perfect innings, so the probability of a perfect inning, right? And from that problem that we looked at before, the probability of a perfect inning, that probability is 0.40. Okay, so what's the probability of 9 perfect innings? Well, that would be the probability of 1 perfect inning times the probability of 1 perfect inning times the probability of the 3rd perfect inning times the 4th, and so on and so forth, until basically we have the probability of a perfect game would be 0.40, again, to the 9th. And if I do that on my calculator, I get that this is a 0.00026 probability of getting a perfect game. Now, there's 30 teams, let's say, playing 162 games per season. This means that we'd expect to see about, 1.3 perfect games per season. However, perfect games are much rarer than that, occurring like once every 4 or 5 seasons on average. So this discrepancy suggests that I should not have assumed independence, but hey, it was fun. So we have this excellent multiplication formula, right? If we want to know the probability of A and B happening at the same time, we know that that's equal to the probability of A times the probability of B given A. Fabulous. But sometimes we want to look for this instead. So this is called our conditional probability formula when we just take our multiplication formula and use the algebra to make it equal this. So in order to do that, I'm going to divide both sides by the probability of A, and I'm left with a formula that says the probability of B given given A is equal to the probability of A and B divided by the probability of A. So this right here is called the conditional probability formula, and this is the formula that's actually given to you on the AP exam, as the multiplication formula is not. But as you can see from the algebra, it's the same thing. I talked about this when we were doing the tree diagram lecture, but I just thought it's so important, I'm going to talk about it once more. Sometimes on the AP exam, what they do is they give you an actual tree diagram, and they ask you to kind of use it to answer a question. So here's an example. Given the chart below, what percentage of youth with good grades are moderate media users? This looks like a big problem, so it needs a 4-step process. So state, what percentage of students who reported good grades were moderate users? Okay, simple as that. Let's move on to our plan. So for our plan, what we want to do is we want to turn this into something that makes sense probability-wise. So we've got to put it into probability language. So in probability language, we want the conditional probability of the probability of moderate users, moderate media users, given that their grades are good. And we're going to be using the tree diagram and the definition of conditional probability. The definition of conditional probability being that the probability of event B, given that event A has happened, is equal to the probability of A and B happening divided by the probability of A. In terms of what we're talking about in context of this problem, the probability of moderate using of media, given that grades are good, is equal to the probability of moderate media using and good grades divided by the probability of good grades. Okay, the do. So for this, what we need to do is we need to follow the tree diagram, and we need to find the probability of good. That's going to be our hardest one. Now, when we look at the tree diagram, we're going to see that good is in 3 entirely different places. So I'm going to remind you how to find the probability of good given that it's in 3 different locations. Okay, so now what we have is we have a probability of good here, and this, by the way, is this number multiplied by this to give me the probability of having good grades and being a light user. And then this good is the probability of good grades and moderate user, and then this good is the probability of good grades and heavy users. So we're going to need to take all of these and sum them up to get our overall probability of good. All right, so when we sum up all 3 of those good scenarios, given light, moderate, and heavy media usage, here are 3 probabilities. When I add them up together, I'm going to find that this added together is a probability of 0.5308. So that's the probability at any given time that someone has good grades. Okay, but I'm not quite done yet. So now I need to find the probability of moderate and good, and that I can just follow the chart in the tree diagram. Oh look, moderate and good. There it is. Okay, so I've plugged that into the formula here, and there's the moderate and good. Here is the sum I came up with, and when I do this mathematically, this is the probability that I get. So the probability of moderate grades, or moderate media usage, given good grades is 0.7942. Okay. So how do I say this in context? I would say about 79.42% of those reporting good grades were moderate users. And then compare this conditional probability with the original information unconditional that 62% of students were moderate users, just to sort of give you a comparison that these 2 events are not in fact independent.